Hi everybody, welcome back to Soft Magnetics.
Hard topics.
I'm Bridget.
And I'm Mike.
And today we're going over a common question we got was how much power can my core handle? So in regard to that, with the help of Mike, we created a new calculator on our website under Tech Resources. And so today Mike's going to go over why we did it, how it's useful, and how it works. So take it away.
All right. Big disclaimer with how much power can my Ferrite core handle. There's a great many factors that go into that the calculator doesn't handle absolutely every one of those. But brief overview of how it works and the materials it's applicable for and shapes it's applicable for. So on the website, there's two different, and we'll show you a quick little demo after this, but just give you kind of a primer on it. There's two different types of geometries that you can work with. There's toroids, because that's nice and easy to calculate things like magnetic path length and cross-sectional area. And there's going to be another tab that says other, or all core types. You'll see what it says in the demo.
We will too.
Where in that one, you kind of have to do a little bit of the legwork yourself in calculating the cross-sectional area and the magnetic path length in the core. Now, once you have that, you're going to have a selection of different materials that you can choose in a little drop-down menu of what you want to calculate power handling for. So the two things that go into it ultimately are the geometry of the core and the material the core is made out of. So you're going to have your material selection. You're next up going to be able to put in your operating frequency and then the dimensions in the toroid calculator, or the cross-sectional area and magnetic path length in the, or winding window area, sorry, not magnetic path length, in the other core calculator. And it's going to spit out a theoretical volt amp limit for the core. Now, how does it arrive at that? So what you're looking at is basically, why we're saying it in terms of volt amps, you're looking at two things to get to that. Your voltage is going to be limited by the flux density in the core at that given frequency. The current limitation is going to be down to the available winding window area. And by that, and talking about a toroidal core, you're talking about the inner diameter on there. That's going to be your constraint as to how much copper or aluminum or whatever you can pack into that. So setting some current density limit inside that window is how you derive the amperage that you could put through there. Again, that's probably something of an oversimplification, but we picked a fairly conservative limit on that current density, knowing that it's imperfect. You can probably do a little bit worse than that. You could certainly do a lot better than that in terms of current density. And yeah, it starts getting really tricky when you start talking high frequencies. But that's kind of the theory behind the current. The voltage and the flux density of the core. So there's going to be a limitation on the core materials that we offer in that as a, in the drop-down menu, because it's limited to the materials where there is where we've measured high flux density power handling, or power loss on the materials. So that's going to be materials like the normal conventional power ones, 77, 78, 95, 96 material, and then some of the higher frequency materials as well. So 61, 67, 80, 79 material. And that flux density limit is not the saturation flux density. At very low frequencies, it is. The saturation flux density will be the limiting factor, not core losses, but you're talking 10 kilohertz, maybe 25 kilohertz in that range. Once you start getting into the megahertz kind of range, or hundreds of kilohertz range, the core losses are going to be the limit as far as the as far as the flux density in the core, not the saturation flux density. So 80 material's got a saturation flux density above 400 millitesla, in practice, you would get nowhere near that before the core losses turn the thing into a good space heater like that. So that's where, just kind of in theory, where some of those limits come from, where the voltage numbers are coming from, where the current numbers are coming from in the calculator. Again, not perfect, but gets you in the ballpark of whether you need a 1-inch toroid or a 5-inch toroid, and kind of get you moving in the right direction.
Cool. All right, so check out the demo now.
As promised, here is a demo of the power handling calculator that we just mentioned. So starting from the Fair-Rite homepage, you're going to go into Tech Resources, Fair-Rite Calculators, and to the right here is going to be a list of the different calculators that we have, or if you want to see the comprehensive list, you can click All Calculators. So the power handling calculator is going to be this center one here. And as we mentioned, this is for giving you a rough estimate in volt amperes of what type of power your particular core is going to handle. So you have the two modes up here, toroid and other mode. So for the sake of this demo, we're going to first start off with the toroid mode. Step one is going to be picking our material grade. So for this demo, we're going to use 80 material. And we're going to enter in a outer diameter, inner diameter, and height of our toroid. So let's go with, let's say, 30 millimeters in diameter, 20 in inner diameter, and a 15 millimeter height. For frequency, now the valid frequency ranges, and this will set some barriers up for you on either side as far as what frequency ranges. If you try to pick something that's out of bounds for that material, it's not going to give you anything. So for 80 material, that's roughly good from 1 megahertz to 4 megahertz for a power application. So let's pick 2 megahertz. You enter in here in hertz, and all the dimensions are in millimeters. So we have 2 megahertz in here, and temperature. So room temperature, we're going to call that 25, and that's in degrees Celsius. Now if we click calculate, we're going to see a little representation of our core up here. Make sure that kind of looks about right, which it seems to. So based off of the maximum flux density that we can handle in this core, you have around 50 millitesla is the maximum. The winding area is 3.14 centimeters squared, and that spits out a number of 5,172.8 volt amperes. Now remember, this is at a very high frequency, when that may seem like a tremendous power number for this size core. Remember, this is at 2 megahertz. They get a lot more kind of reasonable as you start getting down lower and lower in frequency with some of the other materials. And we can try that in the other mode. So if we switch over to other mode, now this is for a geometry that's not a toroid. So what you're going to be doing here is entering in the cross-sectional area of the core. So in the case of something like an E-core, you would put in that cross-sectional area of the center post. And then we're going to be putting in the winding area, which is going to be one of the two windows of the E-core if you're kind of viewing it face on. So for this one, let's do 78 material. Let's do this at 25 kilohertz. 25C temperature. And let's see, we want to do, you know what, for the sake of it, let's enter in our same dimensions. So let's say we have a 3.75 centimeters squared cross-sectional area. And for the winding area, let's go with, again, the same 3.141 centimeters squared. And then hit calculate. And you can see, same core parameters. This is obviously not right. It's not a toroid, but kind of undefined. These dimensions are right. And for power handling, you see how dramatically that drops down from lowering the frequency. Even though this is able to operate at, kind of a similar flux density, we're not getting anywhere near the amount of power because of the lower frequency. So hopefully that's enough of a demo to get you started with this calculator.
Thanks for joining us. Come back soon. Mike and I are both going to be at the EMC SIPI, so if you're at the booth, come by, see us, and maybe we'll interview you for the pod.
We'll sign autographs.
No.
No.
Bye.
Bye.